Hi everyone, I'm Derek Sutherland. I'm the VP of R&D at Realta Fusion. We are a startup fusion energy company located in Madison, Wisconsin, developing axisymmetric magnetic mirrors. So we'll start off with a company update as far as our investments to date and where we're going next. So we've raised between around $60 million of investment to date, with our latest equity financing as a $36 million Series A in May of 2025, led by Future Ventures. We're currently operating a device called WHAM, which I'll show in the next few slides, and we're using those data to validate our real twin simulation codes that are being used to design our next scale-up devices that we're targeting first plasma in 2028 to 2029. Our roadmap is towards deploying the first-of-a-kind fusion power plants in the 2030s. So magnetic mirrors, as a basic concept, is a form of magnetic confinement fusion. And I like to start with one of the simplest approaches to fusion, which is a straight tube full of magnetic fields that you're using to confine a hot fusion plasma. You basically make this with external coils wrapping around the outside of a cylindrical pipe, and those field lines constrain the motion of those particles perpendicular to the magnetic field, but it does not constrain it parallel to it. The drawback of this approach, where it's just a straight pipe with no gradient in the magnetic field, is that the device would have to be quite long, on the order of 100 kilometers, to actually allow for achieving the fusion temperatures in the core of the plasma. And so effectively, some method of plugging the ends of this tube is required. And that's where the mirror force comes into play. So the basic physics principle behind the magnetic mirror is that you are creating a gradient in the magnetic field with external magnets, which in our case are high temperature superconducting coils. This gradient in the magnetic field applies a force to these charged particles because each of them are basically baby magnetic moments that are causing the particles to bounce back and forth between the mirror turning points. And so because these particles bounce back and forth down the length of this pipe, it's reflecting between the two turning points, hence why the mirror gets its name. Though this is a very effective way of plugging the ends of the device and making sure that it stays much more compact, it's not a perfect confinement system, and some of those high energy particles leak out the end. And so we basically need to make sure that the confinement is good enough for getting to net gain, but it's never going to be perfect, nor do we want it to be perfect. So some of the key selling points of magnetic mirrors is that they are continuously operating systems using those external superconducting coils to provide the magnetic fields for confinement, but also that there's no appreciable amounts of plasma currents. What that means is that there's no big disruption risk, which is one of the main outstanding physics risks of plasma current carrying devices like tokamaks. But besides those two features, which are shared with stellarator devices, our differences are quite stark compared to those other bigger machines. One is that cylindrical form factors mean that it's a much more modular and scalable system. Instead of having a toroidal-based fusion system where you have a plasma donut, you're keeping it straight, and so you're able to basically separate the device axially, do maintenance on it, and pull it back together. And you can also change the power output of the device by adding more modules to the length of the machine. And so what we think this translates into is a much more commercially attractive product that's both modular, scalable, and more maintainable. So going one tick deeper in the physics here of mirrors, as I mentioned, one of the challenges of mirrors is that even though the confinement is quite good out the ends, and you can improve that by going to higher magnetic field strengths, there's still a loss cone present where you have very energetic particles that still stream out the ends. We rely on this physics to actually exhaust the helium that's produced from fusion to keep the plasmas clean, but we have to make sure that the losses aren't so large that they end up precluding a high gain scenario. And so the loss cone physics basically means that going to high mirror ratio, where the mirror ratio is the maximum magnetic field you apply with those HTS magnets relative to the minimum magnetic field in the center of the chamber. As you go to higher and higher mirror ratio, the loss cones get smaller, and that means you get better and better confinement. The other big aspect of mirrors is that the double product, so that's the density times the confinement time, which is two parts of the triple product that most people are familiar with. This in tau scales as the ion energy to the 3/2 power and the log of the mirror ratio. So what that means is going to higher mirror ratio improves confinement, as we already mentioned, but also going to higher ion energy actually improves the confinement as well. This is great for fusion because fusion requires very, very high temperatures. So the physics of mirrors means that as it gets hotter, the confinement improves, and it's a positive feedback to get to those fusion conditions. This is exactly the type of physics scaling that you would want to make a fusion power plant based on it. When we look at how the Q of the mirror shakes out in terms of ion energy and log of the mirror ratio, we see that it scales basically as EI to the 1/2 power and the log of the mirror ratio again. So that tells us basically what the ion energies we need to be at in order to maximize the scientific gain, which then when you include all the other inefficiencies in the system like thermal cycles or other loss terms, that results in a net electric being high enough for net electricity production. So the takeaway from this slide is really to get to high gain in a mirror system, you need to go to high mirror ratio and ion energy, which in a way that maximizes the fusion reactivity. So the scaling law is very favorable for mirrors, and we know how to get to good enough confinement. But there's also another bit of physics that improves the confinement even further, and that's something called the ambipolar potential that arises in mirrors. And so when I talk to other people about different approaches to fusion, mirrors are often cast as a form of magnetic confinement, but truly what they are is they're a form of magnetic confinement that's being augmented and enhanced by electrostatic confinement as well. This ambipolar potential results because the ions and the electrons leave the mirror at the ends of the machine through those loss cones at different rates. The electrons go out faster than the ions. So when you're starting up one of these machines, because there's an imbalance in the charge of what's leaving the ends, you end up building up this electric potential to maintain no net electric current conditions out the ends of the machine. This is something called the Pastekov potential, and we know that the voltage of the plasma basically scales as around the electron temperature, in particular about 5.5 times the electron temperature. So what this positive electric potential does is that those electrons that would continue leaving out the ends are instead attracted back towards the confinement chamber by that big positive potential, because unlike charges attract each other. And so what this does is it enhances confinement even more and provides pathways to a high gain design point. So all of this sounds great. You have a simpler form factor, no big risk of plasma current disruptions. Everything seems more scalable and maintainable. So what's the catch? What's the main physics risk? The main challenge of mirrors, especially axisymmetric ones that we're pursuing, is that out of the box they're interchange unstable. And so what interchange modes are is that they're a form of MHD, magnetohydrodynamic instabilities, and when these become unstable, they tend to degrade confinement quality. And so what you have to do is you have to stabilize these modes in order to achieve that really good confinement potential of a mirror. There's a couple ways of doing that. One of the legacy ways is to create these so-called minimum B configurations where you're using non-axisymmetric coils at the ends of the mirror to create a MHD stable magnetic topology. The drawback of this is that it introduces neoclassical transport, which basically means that the really good confinement prospects of a mirror when it's stable, you've now degraded it in the pursuit of making it stable. And so though we think a mirror like this would still work and scale, it's much more complicated and we think would make it much more challenging to commercialize. So instead, we're planning on using active stabilization of this interchange instability using shear flow or vortex stabilization in our plasmas. And so by doing this, we can keep the axisymmetric form factor and all the great commercial attributes while still having a stable plasma and having good enough confinement for a power plant. So the simple mirror is when you have two magnets on either end. That's the mirror that we're currently operating at the University of Wisconsin. That'll show in a few slides. But it's also the mirrors that, a lot of the mirrors that have been designed in the past as well. However, when we do the best case scenarios for those mirrors and we scale up to Q, we see that the maximum gain of a simple mirror is around a Q of 1. And so you can use that to make a lot of neutrons, you can use that to make a lot of fusion power, but it's not quite high enough when you include all the other inefficiencies in the system to get to a net electric power output. So in order to get to that point of making a power plant, we're taking a simple mirror and we're stringing 3 different simple mirrors in series in the same machine. What we call this is a tandem mirror, where we have 2 simple mirrors running alongside the center cell, which is where most of the fusion is happening. So in this graphic, you see that these 2 simple mirrors on either side, we call these the in plugs. And basically what you're doing there is you're driving this with very intense external heating, with neutral beam injection, electron cyclotron heating, and you're building up that electric potential to a higher value than it is naturally in the center cell. And so by doing that, the ions that would be leaving out the loss cones of the center cell would end up getting reflected back into the center cell by that now higher positive potential on the outside. So this allows us to enhance the confinement of the mirror system even more, so you get a factor of 10x improvement in tau at the same ion energy. What that means is that a maximum gain of one system turns into a maximum gain of 5, 10, 15, or even 20 plus. And so that's high enough to make a fusion power plant. So for Realta, the product we're working towards is a tandem mirror, which is 3 simple mirrors linked in series. And that's what we call the hammer class of devices. So going more into our why now? Why are we doing mirrors? These are not new ideas in the sense of the mirror was one of the original fusion concepts, along with the stellarator and also the tokamak. But there's been a series of big advancements in mirror and technology physics that's really allowed us to reconsider these in a serious way for commercialization. So one of those is the HTS magnets that are really being pioneered by Commonwealth Fusion Systems for fusion use. And these allow you to run at 2x the field possible with LTS technology at much higher temperatures as well, which reduces your cryoplant needs. This is a game changer, not just for mirrors, but all of magnetic confinement fusion that uses external magnets. And you can think of this because that the fusion power density scales as beta squared, which is the normalized plasma pressure, times b to the 4th power. So if you double the magnetic field strength, you go up 16x in the fusion power density. That means you need a lot less plasma in order to make a lot of power, much more compact, commercially scalable machines. The other big advancement was really pushed internationally in Russia and also in Japan using vortex stabilization for suppressing interchange in axisymmetric mirrors. And so this really was looked at first outside of the US, and we're using this biasing scheme on WHAM to drive these sheared flows to stabilize, and we're seeing this working quite effectively. What this allows you to do is to stabilize those interchange modes we were talking about before, but maintaining the axisymmetric form factor, which also gives you access to high mirror ratio. So all of these synergistic effects, a better performing product, more simple and better to commercialize, full stop. All of this pioneering advanced stabilization schemes allows that to happen. The last part are these advanced heating systems, so modern neutral beam injection, ECH and ICRH systems. We're using this cocktail of different approaches to heat the plasma that we think will result in the best performance. Currently, we're using neutral beam injection and ECH, and later this year on WHAM, we'll be fielding the first ICRH system to kick up the ions to even higher energies in WHAM. So I've been talking about WHAM quite a bit. Here's a picture of the machine. It's not just pretty pictures. It is real hardware being built and operated right now. This is a baseball card of WHAM that you're seeing on the right there. We're using 2 HTS magnets built by Commonwealth Fusion Systems. These have a maximum operating field of 17 Tesla. We're able to scan the mirror ratio by changing the strength of the magnetic coils in the middle there that are made of copper. And so by changing the currents in those coils, we can change the field strength and tune the mirror ratio accordingly. The length of the mirror between the 2 HTS magnets is around 2 meters, and the plasma radius at midplane is around 10 to 15 centimeters, again dependent on the mirror ratio that you're running at. We're using a neutral beam injection system for our primary heating system for the ion injection, and so this is 1 megawatts, 25 keV neutral beam energy. And then we're also using ECH, which is around up to about 600 kilowatts of heating into the electron channel at 110 gigahertz. And as I mentioned, we'll be adding this 1 megawatt RF system that will be targeting around 26 megahertz nominal frequency to kick up those ions. And so as a testament just to the modularity and the simplicity of this approach, we received these magnets from Commonwealth Fusion Systems in July 1st of 2024. And then within 14 days after that delivery date, we had first plasma in WHAM. So that includes the cool down and field ramp up time of those magnets. So this is just a testament to how simple these systems are and how quickly we can move at Realta to make great progress. Since then, we've been operating WHAM in both HTS mode with these high-temperature superconducting magnets, and we also have another set of copper magnets that we've been running with lately, which allows us to have a different mirror ratio regime of data that we can use to better validate our real twin simulations as well. So on that front, beyond the experimental physics aspects, we also have a state-of-the-art simulation suite called Real Twin, which we believe is one of the, if not the most sophisticated mirror simulation suite ever constructed. So within this ensemble of codes, we have a series of different buckets of physics. So one of those is equilibrium. So this is Pleiades. This is a MHD Gratcher frontal solver that's solving for Newton's second law, F equals ma equals 0, and solving for what the mirror equilibrium looks like. We then take that equilibrium and we plug it into our bounce average Fokker-Planck transport solver called CQL3D-M, which M is the mirror customized version of this. This is working very closely with our collaborators at Compex, and this is how we know what to expect in terms of performance, in terms of like an NT tau perspective. Then the question is, you have this equilibrium, you have these transport properties, does that equilibrium stay put? And that's where plasma stability comes into play. So we have an ensemble of different codes, both for the MHD side of the house. So we're using Nimrod and MUG, which are extended MHD solvers, to look at more of that fluid-like instability, like the interchange modes and the ballooning modes. And then we're also using some kinetic modes, like VPEC, to look at different kinetic modes of interest, like the drift cyclotron loss cone instability, and also the alpha and ion cyclotron instability. Both of these suites of codes are used to really nail down what are the stability properties of our mirrored plasmas. The last buckets here are really focused on the neutral beam deposition, which is one of our main heating systems, and then also the RF wave coupling. So this is for ECH and also ICRH that we'll be bringing online soon. Those are also through collaborations with Compex and MIT using the full wave aorsa code. So the point of Real Twin is to really take engineering inputs in terms of the plasma heating specifications, plasma stability actuators that we're using, like in-ring biasing, and the magnetic coil currents and locations, and then run it through this code suite to then generate the physics output of interest, such as the power, the fusion power output, the power gain of the system, the Q, the triple product, the confinement times, and also generating the synthetic diagnostic signals that we can then directly compare to the experimental measurements on WHAM to make sure they're in good agreement. This is really the process of validation that is so important for making sure that you can trust your codes to then use to design future devices. So to finish up here, I'll give you a good taste of the why and what we're doing now. Let's discuss now the path forward. And so we're continuing operating WHAM, and we're pushing that into the advanced performance regime as we speak. In parallel to that, we're designing our next stage device. We'll be de-risking a lot of subsystems as part of an ANVIL project focused on getting the neutral beams ready and the magnets ready and other feedback control systems ready, along with the facility site itself for the HAMMER machine, which is our next large-scale fusion device we'll be building at Realta. This HAMMER DD device is a full tandem mirror at commercial scale that will be endeavoring to generate NT tau triple products in the center cell in excess of 10 to the 21 keV seconds per cubic meter with an ion energy above 20 keV. For the discerning reader, if you put that on the triple product plot, that is Q equals 1 net equivalent conditions in DD, and that is the goal we are setting for HAMMER DD. The reason why it's DD is that we're keeping with deuterium for the next stage machine to reduce the capex of not having to deal with tritium, but also to avoid having to build larger magnets and other systems in order to tolerate a higher neutron flux. We can really take out all the remaining physics risk of the mirror in this device, show that it scales, and then we'll be in a position to then switch to DT machines, which is what we're targeting for our first of a kind fusion power plants, with HAMMER DT targeting first deployments in the early 2030s. So I've alluded to these attributes of the mirror, but I really want to drive this point home, is that the mirror is a uniquely modular system in the Fusion landscape. You could think of the approach to the product as really two SKUs. You have an in-cap unit and you have a central unit, and those in-cap units are largely fixed, independent of your power output of your system. And so if the customer comes up and says, you know, I don't want 50 megawatts, I want 150 megawatts, we can drop in additional centrocell modules in order to increase the power output of the machine while those in-cap units stay fixed. And so then we can also keep going, and we can scale that in parallel all the way up to gigawatt class. We think for a single unit, the sweet spot for these types of systems will be anywhere from around 100 megawatts up to about 500 megawatts per system, and we're targeting, you know, different lengths of the system to generate those different power outputs. But then if you want to go to gigawatt class, you build multiple units of those in parallel at a single site, and you can really get up to multi-gigawatt class no problem. And so when we think of where this fits in the landscape, we think the mirror is uniquely positioned to go small power outputs, large power outputs, and everywhere in between. And because of the modularity, we really can service customers at a competitive price point at really any of these power outputs in that power range. And so whether we want more central units to get up from 100 to 500 or more cylinders in parallel to get up to gigawatt class, we can do it all at Realta. Really appreciate your attention. Thanks for listening about the mirror. And if you're interested to learn more, please visit our website, realtafusion.com. Also, we're in Madison, Wisconsin. If you want to come visit us, we'd be happy to give you a tour. Thanks.